W Physics. I'm Mr. McConnelly. Today we're going to focus on the electromagnetic spectrum. Now the electromagnetic spectrum encompasses some things that you're very familiar with, like visible light, and then there's a variety of other waves that all appear on the electromagnetic spectrum. Now electromagnetic is a type of wave, and what it basically is electricity, which is a transverse wave, is happening at the same time as magnetism. So you have a magnetism wave and electricity wave, and my picture doesn't show it at all. What I was trying to show is that the electricity waves, we'll say, are this way, and the magnetism waves are perpendicular, zigzagging back and forth. And those two things interact with each other to produce, or they are the definition of electromagnetic waves. So on the electromagnetic spectrum, this is exactly from your physics reference table. And what you'll see, and I'm going to point out a bunch of things on here, but what you'll see first of all is that there are wavelengths. These wavelengths, you'll note, are getting larger in this direction, smaller to the left. You'll also note on the bottom you have frequencies. But the frequencies work in the opposite direction. In other words, larger is to the left and smaller is to the right. Now, the one that you're most familiar with is visible light. And visible light is right here, but notice it's a cutaway. So actually, visible light is a very narrow band between those two red lines that I've just made. Visible light only is right here. Everything that you can see appears right here in this wavelength and in these frequencies. Now, they break it down a little bit further here, and you see that these are all to the 14th. So all of these down here, all of these numbers are frequencies. So when we do some physics problems, you'll notice that you might have to solve or use a specific color, and you can get the range of its frequency from this table right here. You can also figure out its wavelength, because you know that everything on this chart, this is a real key concept here, the velocity of everything on this chart is 3e8 meters per second. Actually, in the reference table, I believe it's written as 3.00 E8, so I'll be exact about that. So the velocity, as written on the front page of your reference table, of everything on this page is 3e8. That means if you know a frequency, and you always know the velocity, you can also figure out the wavelength using what equation?
V equals F lambda.
Yeah, everyone's saying V equals F lambda. You know the velocity is always going to be 3e8, so if you know one of the other things, you'll be able to solve for the remaining one. Now let's just break down a few of these. If you like to tan, you are going to focus ultraviolet light on your skin. Okay? Now, basically what I want to say is that things to the left of visible light become more and more dangerous to humans. So, ultraviolet light is marginally dangerous, and if you expose yourself to enough ultraviolet light over enough time, sometimes you will have issues with that. You could get skin cancers. Your eyes actually are damaged by ultraviolet light, so over time that can be damaging. Ultraviolet. It's an ultra, the way to remember it is that ultra meaning, see, notice this is written red to violet over here. This is a little bit higher than violet, so it's ultraviolet. It's just a little bit past that. And you'll also notice that most people realize that if you get a lot of x-rays, that can be dangerous for you. So you go to the doctor and you get an x-ray, and they don't let you get x-rays all the time, and when they give you x-rays, what do they put over a lot of your organs? They put a lead vest to protect you from the x-rays, so the x-rays are only focused on what they're trying to focus on, not on the rest of your body. But notice, I don't think most people realize this, X-rays go from here to here, which overlaps ultraviolet. Okay? So ultraviolet and X-rays, there's actually overlapping parts, so you can start to think, yeah, I guess I understand why ultraviolet can be dangerous for me. Okay? That same occurrence happens with gamma rays. Now, everyone that's heard of gamma rays is thinking like nuclear facilities where they make nuclear power plants, nuclear bombs, and they know that there's gamma rays in those, and they know it's a bad deal. It's really not good for you. But again, that overlaps with X-rays. So when a bomb goes off, a nuclear explosion, there's X-rays, there's gamma rays in there. Okay? Moving to the, we'll call it the safer side, is things like infrared. Now again, going back to here, since red is over here, if you're a little bit more than red, you are infrared. And infrared is, the prime example would be, if you have a heater unit on the other side of the room, you can feel the heat. How does the heat get from the heater unit to you? Well, a lot of it's through infrared. And that's the same with the sun. You can stand outside on a sunny day and you feel the sun warming you up. And how can that happen since it's millions of miles away? That's infrared waves. It'll actually travel that way. Now the next one, microwaves. Microwaves is commonly confused by physics students because when you hear microwave, you're thinking of the box that heats up your food. Well, that is a microwave. But what we're talking about is inside the box that heats up your food, the wave that is actually heating up your food. Let me be more clear. Inside a microwave, the box, you put your plate in there and you want to heat up your dinner. When you turn on the microwave, it sends out microwaves. That's just because of the size of them. That's why we call them microwaves. It sends out microwaves, and those microwaves actually resonate, yesterday's lesson, they resonate water molecules. So what is resonating again? It's when you cause something to vibrate at its natural frequency and the amplitude gets larger and larger. So it starts vibrating in a very aggressive, energetic way. Microwaves vibrate water molecules in food. If they start vibrating enough, they get hot because of the friction. That's how your food heats up. If you stick something in the microwave that has no water content, it doesn't heat up because microwaves vibrate water molecules. I don't know if you knew that, so that kind of clears that up for you. Here's another one. There's all sorts of radio waves. Actually, the rest of the chart is really radio waves. And these long radio waves, an example, a way that you might use them, is if we have a submarine on the other side, a United States submarine on the other side of the world, and we're trying to communicate with it. The way we communicate with it is long radio waves because the wavelength is so long, they can actually pass right through the Earth and get to the submarine on the other side. Whereas, if you listen to your radio and you're listening to your favorite station, which is probably an FM station, I'm guessing, if you listen to your favorite FM radio station, you're talking about radio waves that are here. That's pretty far removed from these radio waves. And these ones are the common ones that are sent. These are the common ones that are sent out and that host most of the popular stations. Now there's also AM radio waves. And I don't know if you know the difference between AM and FM, but what AM means is amplitude modulation. Amplitude modulation. So what you're doing, amplitude is how tall the wave is, right? If you're listening to AM radio, you are listening to waves that the difference between the station 590 and the station 810 is a difference in amplitude. They have modulated the amplitude. Whereas if you're listening to FM radio, can anyone guess what that might be? What are you modulating?
Frequency.
Yeah, you're modulating the frequency. So, when you listen to different FM stations, they have different frequencies. And you kind of knew that because they always say 107.7, 92.3. That's your frequencies that they're talking about. And they're talking about those in megahertz. So, that's kind of a quick summary of the electromagnetic spectrum. The key that you want to take away from this is that everything on this chart travels at 3e8. If you can keep that in mind, that's going to solve a lot of problems for you. For today, physics.